In this problem, we're given a model for per capita coffee consumption in gallons. This is a yearly per capita, so this is how much this function estimates how much coffee has been consumed since 2002, and that's what the value of t is. So remember, the number of years since 2002 means that we represent the year 2002 with a t value of 0. So 2003 would be t equals 1, and so on. We're going to estimate a rate of change, how quickly coffee consumption is changing, but before we do that, we're actually going to build a little table. So this is the setup for the problem. And we're told to build a table that contains the inputs as the years and outputs, which are the gallons consumed, for input values that are within 0.5, 0.1, and 0.01 years of 2008, before and after. So we're going to have our T, and then we're going to have our C of T, our consumption. And what I've done is I've set up the equation in my calculator under y equals, so there it is, negative 0.08 t squared, etc., etc., etc. And I'm going to use an easy way to get my outputs out of this function. I'm going to do vars in my home screen, y vars, function, y1, and I'm going to evaluate y1. That is the equation that I have in there. I want the output when the input is, well, first of all, let's find out what it is in 2008, because we're going to need that value. So what t is that going to be? Well, since 2002 is t equals 0, 2006 is 6 years later, so that would be t equals 6. So if I do 6, and I compute that, I hit enter, that's going to be 24.07. So for t equals 6, I'm going to have 24.07. So that means that on average, people consumed around 24 gallons of coffee a year. Now, some people consume more, some people consume less, or none at all, but this is just taken per person. This is how much, if all the coffee consumption were distributed equally among all people, then each person would have had 24 gallons, or just a little bit more. Now, I am going to be careful in my rounding, because I know that using instantaneous rate of change, or that idea, is going to deeply be affected by rounding error. Okay, so I want input values within 0.5 years. So that means if I have 6, I want to look at 5.5, and I want to look at 6.5. Very important, because you want to make sure that you're considering stuff that's happening on either side of that. So I'm going to hit second enter, pull up my screen so I don't have to type in the vars thing again, and I'll do 5.5, which gives me 24.26. And then I want to do 6.5, so I'll just go here and change my 5 to a 6. That gives me 23.84. And then I also want to do 0.1 years of 2008. So that would mean 5.9, and let's see, that would be 6.1. And then I also want to do 0.01 years of 2008. So 6 minus 0.01 is 5.99. So it's like taking a cent away from $6, or adding a cent to $6 would give me 6.01. So I'll do those really quickly to get the table complete. And so I want to do 5.99. You can do these in any order you want. It's not necessary that you do it this way. And now look at my rounding. I'm going to make sure that I round this out to as many decimal places as I see. Oops, I guess we should have done 5.9 first, but that's okay. 24.074192, and then I'll just do 6.01 since I already have 3 digits here. 6.01 gives me 24.065,792. Now notice that how close these numbers are to one another, because they're not very far away from my destination point. And then I want to do 5.9, so I'll hit second enter, and I want to do 6.1 as well. So I'll do 5 point, delete that, change that to a 9, and I have 24.1112. Then I'll also do 6.1. change that to a 1, and I'm going to change this to a 6. See how quick this is. I know there are faster methods, but this method will pay off here pretty shortly. And that's 24.0272. Okay, so it wants us to build a table, and in part B we want to find the average rate of change between the input of interest, so that's this guy, and I'll box that in because we're going to be comparing all these points to this guy, and each of the fractional years found in part A. Note, you can think of decimal years as being the estimated per capita consumption of coffee at that particular point in the year. Okay, so we're going to find the rates of change between these. Now I built a table, so I would end up doing from 6 to 5.5, I would subtract these two, and from 6 to 5.5 I divide it by, so change in consumption per change in time. So we're going to have per capita, or sorry, I won't even do that. I'll just do gallons. So it'll be gallons per year. Gallons divided by years. So rather than to have to type these long numbers in, one thing I could do is go back and reference the fact that I know that this guy's y of 6, this guy's y of 5.5, and I can just do my rate of change all that way. But since I have them written down, I suppose I'll just go ahead and type them in. 24.07 minus 24.26 divided by, oops, parenthesis, divided by 6 minus 5.5, which is 0.5. You could type the whole thing in, but it saves us a little bit of time. And it's negative 0.38. So we get an estimate of negative 0.38 gallons per year. So initially it looks like the per capita consumption is actually going down right around 2008, but let's actually see what's happening in 2008. So we're going to get a little bit closer. We're still going to do 24.07 on top, but now we want to compare it to this point, and this point to this point. So we're going to have 24.07 minus 24.11. I'm going to insert a 1 and a 2, and now the difference in the inputs is a tenth of a year, 6 minus 5.9, and I find that that's negative 0.412 gallons per year. And I do the same thing for 5.99. Second enter. So 5.99 has an output of this long, ugly looking thing. 24.074192. Divide that by, well, what's the difference in time? It's 1 cent, 1 penny, so it's 0.01. And we get negative 0.4192 gallons per year. So beforehand, it looks like the coffee consumption is dropping. So what would our estimate be? Well, our estimate would now be, well, since we're this close, it looks like it's decreasing by somewhere around maybe 0.42 gallons per year, since that seems to be where this is going. It's there's a bigger drop here, a smaller drop here, and now we're at 0.42. Okay, so now we do the same thing but from the other side. So I'm going to put question marks here. We think this might be the answer, but we're not sure, so we're also going to compare it to points on the other end. And so we get, clear this, second enter, 24.07 minus, oh, let's do it from the other side. So 24.06, try that again, 0.065792 minus 24.07. And now we're taking 6.01 minus 6, which is about 0.01, which is 0.01, excuse me. And it looks like we get negative 0.4208. Okay, well, we could keep going, but it looks like our negative 0.42, which we believe to be the slope right around that point, seems to be pretty accurate, because look, it's negative 0.4192 over here, and then as we look at points after that, it's negative 0.4208. So what's in between these two guys right here? Well, it looks like negative 0.42 gallons per year. So that might be the answer that we estimate. So at that moment, at the beginning of that year, it looks like the drop is about just under half a gallon per year of coffee consumption per person, which, depending on who you are, you might think that's a good thing or a bad thing. Represent these rates of change graphically by sketching a copy of the curve and then sketching the corresponding secant lines. Okay, so what would this look like? There's my y equals, there's my equation, and now I go to graph it. Well, as a review on graphing, we want to make sure that we include, this is a quadratic, so the vertical intercept, so we want to make sure that we include the point 23.71, and it has a negative value of a, so it looks like it's going to be going down, it's going to be decreasing. So what I'll do is I'll just set my y max, whatever it might currently be, to about 24, because I know that's the highest point. Y min will be 0, just for lack of better things to choose. And let's just go from 2002, that's 0, to t equals 2012 maybe, just so we get a nice image of what's happening. And so we kind of see we kind of see that part of the curve right there. We see we kind of missed a little piece of it. So let's go up a little bit. Change our window setting to maybe 25, 26. So we get that top part of the curve, and there it is. So how would we actually represent this? Well, without me drawing it, I mean, you can kind of figure out that we're looking at time equals 6. So 1, 2, 3, 4, 5, 6. So right there, that's the point where we actually want to know what's happening. And we can see that it's going down. So we're picking this point and a point that's half a unit over and connecting them with a rate of change, with secant line. And we're taking 6 and we're connecting it with 5.9. And then we're taking 6 and we're connecting it with 5.99. And so we're doing this also on the other side with 6.01, 6.1, and 6.5. So if I were to try to just quickly replicate this without spending too much time on it, there's 6, and there's 5.5, and I find that slope. And there's 5.9, I find that slope. And there's 5.99, I find that slope, and that slope, and that slope. Then I find that it appears to be about negative 0.42 as the true slope at the point of interest. Part D, from your rate of change table in B, what do you estimate the instantaneous rate of change to be in 2008? In other words, what is the limit of the slope in 2008? I think we've already established that. We established that it was negative 0.42. And interpret your answer in C in the context of the situation by using complete sentences. So, we estimate that in 2008, the coffee per capita coffee consumption is decreasing by 0.42 gallons per year. Now, one thing to keep in mind is, will it always be decreasing at 0.42 gallons per year? No, not according to this model. It looks like the actual decrease is not constant. It looks like it's actually going to start dropping at a faster and faster rate based on the data that we have available. So this is just an estimate of what's happening as a snapshot at that moment in time.